All right, so the bulletproof press is just something I got off the internet to demonstrate that you can't change things with these mutability wildcards. But basically, I'm going to talk about, there's two mutability wildcards in D, const and inout, and I'm going to go over how they work, what they're used for, and talk about some issues that we have with inout specifically. So likely everybody knows this stuff, but just to give a base, mutability is the ability to change something in place. So we change x, and we have a pointer to x. If you change x, it's the pointer, the value that the pointer changes to, yes.
Please, could you please read the URL of your slides for those folks who are watching but not following Twitter?
Read the what?
The URL of your slides.
Oh, I'm sorry.
On the first.
Yeah, so I just threw this up there. Andre said to do this, but this is a place where you can download the slides. It's http schveigai.com/DConf2016.pdf. Good? All right. All right, so yeah, if you change x, then what p is pointing at also changes. So basic mutability. So immutable in D is guaranteed by the compiler. We do it with the immutable type modifier. The type modifier basically tells the compiler how to modify the type that it's inside the parentheses. So in D, you can circumvent immutability, but it leaves your program in an undefined state. So you probably shouldn't. And the compiler helpfully doesn't let you do that unless you use a cast. Tail modifiers is something that, in D1 we didn't have them, but in D2 we have them. Basically, you're modifying what a pointer is pointing at or a reference is referring to. So in this case, px is an immutable pointer to an immutable integer, and mpx is a mutable pointer to an immutable integer. So we can change mpx and have it pointed at another immutable piece of data, but we can't change px. You can think of the pointer itself as the head, and what it's pointing at is the tail, so that's why we call it a tail modifier. Sorry. Anytime you use a type modifier, it's a transitive thing. This applies to immutable, const, inout, and shared. So anything, if we have an immutable s, the type of s.x is immutable, and the type that y points at is also immutable. So it's turtles all the way down, as Walter likes to say. And this also means that the compiler will prevent you from having an immutable pointer to mutable data, because that would violate the promise that you can never mutate it. The only exception here, of course, is mutable, which is the default, is not transitive, which I don't know that that would ever work. So the first wildcard we come to is const. Const indicates that you can't modify it through that reference, so it's like a temporary immutability. Const, because of that, can refer to both mutable and immutable data. So here we have a const pointer, or a mutable pointer to const data, and we can assign it to point at mutable data, we can assign it to point at immutable data, and it works just fine. Because it could point at immutable, you can't change anything through that pointer. So then we have const function parameters. Arguments passed to const parameters can't be modified while they're inside that function, even if the original parameter is mutable. I believe in C++ you can cast, if you know something is mutable, you can cast away const and modify it. That results in undefined behavior in D. So the nice thing about this is it can accept any type of integer, const immutable or mutable data, and we have the same function call. So why would you use const? The nice thing about that is the function signature itself advertises the guarantee. There's no need for you to read the function and find out if it actually mutates that data because the compiler is guaranteeing that for you. It's always available as a wildcard at any point, not just a function call. So this is one benefit it has over inout, which only is a wildcard at a function call. There's only one function implementation emitted by the compiler. What I mean by that is, if you have you could do the same thing as const with a template. You could have a template that accepts a mutable int or an immutable int, and it would have the same code inside, and the compiler would actually emit two different functions, and they would be identical code-wise. But when you have a const, it's not a template. It only emits one function. And also, unlike templates, virtual functions are allowed. So you can specify as a base class the parameters to the derived classes can't change anything in the class if you put a const tag on the function, or if there's any other parameters, you can specify that in the base class. Where const fails is if you're doing an accessor. So if we have this struct s, and we have a private integer we want to expose, if we wanted to make this work for const s, or immutable s, or mutable, you'd have to write three functions. Note that the const and immutable at the end of the function there is basically a modifier on the this pointer. So that's what that is. They're also known as const and immutable functions. Note that even though we have this here, and it looks like the same code on the side, they're all going to generate exactly the same function. But we still don't have a guarantee that if you called the x function on a mutable s, that it wouldn't modify the underlying container itself. So we lose that advertised guarantee by having to do it this way. All right, come on. All right, so this is the other problem with const, is the double indirection problem. So you have, this is kind of hard to follow here, but if you allowed the line where it says error, basically the type of *pp and IP is the same. They're both const int pointers, or mutable pointers to a const int. So it would allow the assignment, and now pp would, or p would point at an immutable int. There's a similar problem with classes. You can't take, like, let's say an array of, let's say you had a hierarchy of animals, cats, and dogs. So you can't take an array of cats and pass it to, and implicitly pass it to an array of animals, because then somebody could go in and change one of those animals to a dog, and then you have a real problem. So there's a way to do this with a template solution. If you use this T template, that basically takes the type of whatever was actually used to call that function. So we can see from the static asserts, yes, it does exactly the same thing as the three function version, but for each one of those, it assumes, oh, you're passing a const s, or you're passing an immutable s. So it works correctly. However, it's a little confusing. There's no real indication of why you would have this T parameter, because it's not used anywhere. But it's shorter. So it does have a way to make the code easier to write. It also doesn't suffer from the double indirection problem. So The next wildcard one I'm going to talk about is the inout wildcard. Now, inout in D1, I know there's a lot of the D1 users in Sociomanic, but D1 has inout to mean it's a reference, and a lot of other languages use that too. But since we have ref in D2, we kind of hijacked inout to mean this new funky thing, which basically allows you to, it wraps the mutability of whatever it is you're type modifying. So inout basically takes the place of const, immutable, or mutable, and then unwraps it on the output. So I kind of like to think of it as like you're wrapping a present or something, and somebody can't look at it till the end, but, you know, and they can't change anything inside it. So this is the way I think about it. You can't actually know what it is inside the function because it's not a template. So there's no way to determine inside X whether this was called with a mutable, immutable, or const struct. These are the rules for inout. Rule number 1, it must act as a stand-in for only one mutability modifier, so it can only be const, const, immutable, or mutable, and actually could be inout as well, we'll see later. Wrapping occurs only in function calls. So inside the function, inout works kind of like immutable, that you can't assign anything to it. It can only take assignments from other inout variables. And the reason that is because we know that it stands for one mutability modifier. Nothing converts to it, and it can't convert to anything else except const. And the compiler prevents mutation. That's, the reason for its existence, and it's transitive. The other restriction is that global or static function variables cannot be inout, because if you called an inout function and then saved that variable when you were calling with a mutable, and then you passed in a mutable next time. It's hard to say immutable and immutable. They sound the same, but anyways, if you called with two different mutability modifiers, then you could assign things that shouldn't be assigned to each other and break immutability. So that's why we don't allow that. By the way, those are the good rules, and we'll get to the bad rules later. The double indirection rule does not apply to inout, which is a nice feature. If you look at this, it works. The reason it works is because it matches, let's say in the first call, it matches mutable, so both can be passed in. It doesn't require a conversion like const would. So if you used const on those two, it wouldn't work. Same thing with immutable. Now, if you tried to pass, let's say, address of P and address of IX, it would not work, because now you have two different, it can't stand in for two different mutability modifiers. And what happens when you do that? Well, if you call it inout with different modifiers, then it basically picks a common modifier between the two. So if you, so this function min p basically is returning the pointer that points at the smallest integer. So we can pass in any combination of these. There's no double indirection here. And if you pass in a mixed variety, the inout unwraps as const. If you pass in a common mutability modifier, then it unwraps as the original one. So the important thing here is, if there was a double indirection issue, you would not be able to call min p on the mixed thing, because first it has to convert everything to const before calling in, and const doesn't allow that double indirection conversion. Okay. So inout can also be something that it wraps. So if you call a function with inout variables, it's the same thing as calling it with const or immutable or whatever, and it just unwraps as inout. So in fact, it's just like a normal function call at that point. You're just passing inout data and getting inout data back. So that also works. This one's kind of interesting. So I think Timon Gear is here somewhere, right? He brought up the point that the inout const can only convert to either const or immutable. So if you look, I have the three substitutions for inout here: mutable, const, and immutable const, all go to either const or immutable. So, because of that, we can implicitly convert any kind of immutable to inout const. And therefore, we have a fifth modifier that also works. And inout functions called with both immutable and inout will wrap and unwrap as inout const. If they have to be, but it is a conversion, so double indirection rule would apply to that. Is there any questions so far?
Hello. Oh, yeah. I've never used D2, but what is const and what is immutable const?
So const basically, if you wrote that and you said, okay, D, give me the type of this, it would say, oh, it's just const. And if you write immutable const, it would say, oh, it's just immutable. It's already done by the compiler. If you write immutable const, I believe it still comes out as immutable const, if I'm correct. But yeah, all I'm saying is that because we can deduce that, well, this could only ever be const or immutable, immutable will fit into that. So that's why it allows this conversion, this implicit conversion. Did somebody else have a?
Thank you. I'm also not a D2 programmer.
Yeah.
It's kind of hard to wrap my head around this. Would you ever use inout, ever, having all these rules and everything?
Right, so the rules are hard to understand, but using inout is actually pretty simple. You just put inout where you would normally put const, and it basically, it's the best use is for, where is it? For an accessor. So basically, I have this data, I want to pull it out, I have a const version of this struct, or I have a mutable version or immutable version. If you wanted to pull out a piece of data and have the same mutability, you would have to have three functions or a template anyways. Yeah, John.
So seeing as when you write inout, the compiler checks that you're not modifying it,
Yeah.
couldn't you have accessor functions kind of automatically be checked to see if they could work with const, and if they do, they just do?
You could do that. You could, do it this way. You can do it the other way. But the thing is, when you put that inout modifier on there, you're telling the compiler, I don't want to allow this to modify. But you're also telling the user, you don't have to read this function, because I'm promising that it's not going to modify the data you pass in. So, we could get away with not having const even. We could get away with having just mutable and immutable, and use templates if you wanted to have a wildcard between them. But the advertisement is really the feature that inout provides. Is that good? All right. All right, where were we? Okay, so just like const, this is a list of reasons why you would use inout. Don't have the double indirection problem. Useful in situations where basically the accessor. The other thing is inout is not a template, so it's still only emitting one function. It's not, building 3 copies of the same code. The advertisement guarantee. And same thing with virtual functions. So a virtual function can be an out, whereas a template function cannot. So these are the reasons why you'd use it. This is kind of a double indirection use case. So if you look at the argument here this is from standard out range pop front for arrays. So if you look at the argument to pop front, it's a reference to an array. So there is a double indirection in there because you have the reference and then the array itself is a reference. So basically if you pass in a const int or a immutable int array or a mutable int array, you're going to get 3 generated functions that do exactly the same thing. All you have to do is put inout on the type, and because there's only one possible match, you will never have a double indirection problem, and it works just fine. I actually did this to all the functions I could find in standard out range, and the code's, the output savings is not huge, but it doesn't count anybody else using their own custom array types that would save from that. And we also are advertising that PopFront does not modify any data in the array. It just gives you a slice of it. So there's that, even though reading the function is pretty easy. Let's see, where's the... Anyways, I have more notes, but I can't read them. So that's one possible case for using double indirection. There's other times that I've had a chance to use inout where it didn't seem like it's something that you could use it on, but it worked out good. So here's one of the problems with both const and inout, is that they're viral. So if you write a function foo that takes something and as inout, if that something doesn't have any inout functions or const functions, you can't call anything on it. Same thing with const. If you took a const t and it didn't define anything with const, it wouldn't work. Now, one nice thing about inout, though, is if you do pass in something that supports const, at least, it will work. But it's going to call the const version because inout implicitly converts to const. So this will compile just fine with S. If S only had the mutable version, it would not compile. So if something supports const, inout kind of devolves into const. If it supports inout, then it's going to give you the best of all the worlds there. Any of those types it would pull out. But you can see somebody who didn't think about inout when they wrote struct S isn't going to enjoy all the benefits. So as soon as you start using inout or const, you got to put it on everything, and that's part of the problem, especially with generic code. So nested functions is another thing that is kind of a sticky situation. Nested functions can access inout data in the outer function. So you can see this function foo takes an inout int x, and then we have a global variable b. So I believe this is a similar thing to that min p or whatever. Anyways, if I took out that version none, it wouldn't compile because if b happened to be at a lesser value than whatever was passed into foo, then you would return an address to b. Now, if what you passed in wasn't immutable, then what comes out is going to be mutable or whatever. So it could violate immutable in that case. But you can pass in inout variables. So basically, fun is not the arguments that are passed to fun are not wrapped like they were to foo or a normal inout function. It's like, and it's only for internal functions that can access the outer function's context. If you made fun a static function, then it would just be a new wrapping of inout, and it would be fine. All right, so delegates and function pointers. This was a common problem when we had opapply that we used a lot. Is opapply takes a delegate that is going to work with your data, and you can't say basically what you want to say here is foo won't modify any data that you pass it, but it might call this function that you give me that knows the correct modifier and can modify the data. So this is kind of like what this function is trying to say, but we don't allow this. It basically it treats the delegate as another wrapping of inout, unfortunately. So here we have inout member variables are not allowed, and because unwrapping of a struct member. So how do you make an S that has a mutable X? You can't, because it's inout forever. So there's no way to wrap or unwrap that data. So we made that illegal, and that's kind of my fault, actually. It's something I suggested that should be true, but the problem is when you start having functions that take template arguments, and the template arguments were inout themselves, and then you try to build an internal struct that you're only going to use internally, you should really be able to make an inout, a struct with an inout variable there, because it's not going to come out of the function. But that's typically not. That's where some of the problems with inout, you try to call these functions that work with everything else, but with inout it doesn't. This is one of the reasons. These are two other limitations that are my fault. The compiler doesn't let you return an inout unless it had an inout parameter. When I first proposed that, it kind of made sense. It's like, why would you just use const or something else? Why are you using inout? But what happens again is that you have, let's say, a template function, and the template type you pass it is inout. So it's generating some piece of data, and you want to return it as inout, but it won't let you do that. So this is where some of the problems happen. Yes, Marie?
Yeah, whether in this case you have an implicit parameter as the context. So you have an inout parameter, effectively. In the case you mentioned, you have an implicit parameter, which is the closure, basically, and this
you're talking about
parameter is inout.
The internal function.
Yeah, so you should be able to return inout from there.
So like this one right here? Is that what you're talking about?
Yeah, but even if you don't take any parameter, there is an implicit parameter there.
Yes, there's an
which is
implicit
the
parameter.
frame of the the outside function.
This other, yeah. There's an implicit parameter, and you could.
It should be able, we should be able to.
Yeah, and
if there is some inout going on in the outer function, we should be able to infer that
I think that's
the
true.
implicit parameter is inout.
I think we can do that too. Yeah, that's one thing that I posted recently that should be doable. But this other problem that we have here is that just a standard function that doesn't have any inout parameters, it's not an internal function, still it won't let you return an inout value because it didn't make sense to me at the time when I proposed it. That's really what it comes down to. And also, if you have a function that doesn't take any inout parameters, you can't just declare any local variables as inout. And a very famous thread that occurred recently, what the hell is inout? Inout int equals 0 is because of that. So I'm sorry. But it's something we can fix, so there's still hope. Constructing inout data. So if you have a structure and you want to create an inout version of that structure, and it has a constructor that you've defined, you can't do it. It needs to have an inout constructor in order to construct it. And the way you would construct it is by saying here, inout s with the data you're passing in. The nice thing is that if you successfully make an inout structure, and it's not too hard, an inout constructor, then it works with any mutability type. So I can define one constructor there, and it works with any form of immutable or mutable or any of those, and it will just return. It works fine. So that's one thing to keep in mind when you're using inout. Again, these are because templates very often you use inout without even thinking about it or without having planned for it. We can fix those two limitations. I'm not a compiler developer, so I don't know how difficult it is, but conceptually I think you should be able to do this. I think Kenji even has a pull request for allowing inout return types for non-inout functions. The other thing is we could allow inout members. So before we said we can't have a S have an inout member, but why not? It's not only, so in bar we see we created an S, but we're inside an inout function, and that S never leaves the function. So it's fine inside there. You just it wouldn't work properly, or it wouldn't work the way you'd want it outside the function. Baz is a little bit interesting because you're constructing an S before you call foo, and Baz is not an inout function. So how would that work? Well, you could, as long as it's in one expression, you should be able to translate the mutability of X through to foo. And again, not a compiler writer. I don't know if that's possible, but it would be nice. But these are things that we could potentially do. So, in answer to your, no, and actually that was a different thing. But the op apply problem, we could actually just allow this. I thought about it. I think this would just work.
May I actually ask a question, Stephen?
Yes.
So having in-out members in a struct, if I see that correctly, it kind of would solve this problem of returning in-out ranges from
I'm
containers.
sorry, I couldn't hear what you were saying, Martin.
This in-out member in a normal struct, would that solve the problem of returning an in-out range from a container? Like, we have this recurring problem. You have a container, it can be mutable, immutable, whatever, and you want to have one function that returns a
Unfortunately not,
struct.
because
Okay.
there's no way to pull the in-out off of that. So that's actually a different problem. That's the tail modifier problem. One of the nice things about arrays, and this is why we don't see this very often because the most common range is an array, is that you can't tell D to just apply a type modifier to the tail part of a general struct. So if I just had a struct X with a S with an inout int star, or I'm sorry, just an int star X, and I wanted to somehow say, okay, I want to be able to modify that pointer, but I want it to point to a const int or an immutable int. There's no way to add that piece to it. So I don't know that we could solve anything. We could solve that problem with this, but it would at least allow you to some of these functions like in place that basically build a union internally so that it can do some funky stuff doesn't work because we don't allow in-out members. So those kinds of things can then work. So yeah, in this, we could just consider the in-outs inside the function pointer signature as part of the same wrapping. So if we call foo and we have a function that takes we pass in a mutable int, and we call a function that or we pass in a function that takes a mutable int, we could just allow it to work. And the only thing that's a little controversial is now you have this function foo that's taking inout data and potentially modifying it. However, foo is also taking the context in which it can modify. So foo itself can never modify the data, but the function you pass it could. So this is the kind of thing that op applies exactly would work with. And I think this would be fine. Currently, to foo, you have to pass in an actual function that takes an inout parameter because the signature has to match exactly. And I think that would still be fine if we loosen that restriction. So that's actually the end. Is there any questions? Any other questions? Yes. Stefan.
So if I understood correctly, the main benefit of in-out is that it allows this double indirection.
Yeah, that's one of the benefits, yeah.
And we can't fix the meaning of const to do this and just drop this keyword?
Right, because const, you have the double indirection problem. If you convert something to const, you can't do it through two or more mutable indirections, because then you would be able to assign something. You could assign a one pointer that points to mutable data to point at immutable data, and then now you've violated immutability. But with inout, we don't have that problem.
Okay.
But that's one of the benefits. Yeah.
As I know, you have default constructors for structures.
Right.
Why do you have to create a constructor if your structure is const or immutable?
Right. In that example, that was just a struct that had a constructor. It was you wouldn't have to create one. If you don't create one, it works fine.
Thank you.
It works fine with inout.
As on the last slide you showed, this example. So there could be a function with the same signature as foo currently that actually relies on the fact that it can call f with const, mutable, inout, and mutable pointers. And that wouldn't be allowed anymore if you allow this. So,
I'm sorry, I didn't catch the question.
So I mean, inside foo, actually it could rely on being able to pass different qualifiers to f.
Right. So inside,
I mean,
the compiler would have to restrict that to only. So it would have to treat f as not a new wrapping of inout, but the same. So you could only pass it inout values. You couldn't pass it anything else.
Yeah, so it's a breaking change. That's what I'm.
Right. Yeah. I see what you're saying. Yeah, I don't know how much this is used. So. However, if foo wasn't taking any inout parameters other than the function, then it could do that. So I guess that's it. Right? Thank you.